Today we're going to be talking about sensor fusion, and that is where you collect data from different types or maybe the same type of sensors, and you have multiple sensors. That data is combined in order to give you a better understanding of the environment around you. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of ML tasks, from regression to vibration and sound classification to object detection and predictive maintenance. You can import data from any sensor and deploy your model to almost any device. You maintain control of the data and firmware the whole time. Edge Impulse Studio is an online platform that handles everything, including collecting data from your embedded sensors, labeling the data, and performing any pre-processing calculations to training the machine learning models. This end-to-end project is called an impulse. You can then test your impulse on live data with a connected sensor. After, the studio will guide you through the process of creating firmware or a library that will run your impulse on any number of platforms. This includes your pre-processing code, trained neural network, and any anomaly detection code you may have so that you can perform inference locally without an internet connection. You are probably aware of some examples of sensor fusion. The first is when you have a device like a smart speaker perform acoustic direction finding. For example, you may own a smart speaker and it uses an array of microphones in order to narrow in on where a speaker is coming from or where the sound from that speaker is coming from. And it does this using some fairly advanced digital signal processing techniques. However, it is an example of sensor fusion because it's taking readings from multiple sensors, combining them, and using it to zero in or hone in on the speaker location. And it does so in order to cancel out all of the sound around it that it might not care about, such as other conversations. Another example is stereoscopic vision. This is when you take two cameras of the same type, you put them together at a known distance apart from each other, and use the information, combine it in a way such that you can get an idea of the 3 dimensions in the space around you. This is an example of sensor fusion using two sensors of the same type. What we're going to be looking at is using sensor fusion to combine sensor data from 3 different types of sensors. Actually, we're going to be using 2, but one you're probably familiar with is this idea of getting absolute orientation using an accelerometer, a gyroscope, and a magnetometer. Many times, advanced digital signal processing techniques or things like Kalman filters are used in order to combine all of this data and get us some type of information out that gives us a better idea of the environment, more than what you can get individually out of the single sensors. In this case, think of a VR headset or a virtual reality headset. It knows where you're looking, how you tilt, and the absolute heading of where you're facing because of the combination of these sensors, and that's an application of sensor fusion. We are going to be replacing Kalman filters and other DSP with a neural network so that the neural network doesn't necessarily care about the types of information that's coming in. It's just trained to take that information and use it to make decisions or classification. In this case, we're going to be classifying a basic magic wand, and we're going to be doing it in a more advanced way, or slightly more advanced way than you might have seen, because we're combining information from both an accelerometer as well as a gyroscope. To start, head to docs.edgeimpulse.com. Scroll down and you should see an entry for the Arduino Nano 33BLE Sense. You'll want to follow these directions in order to install the Arduino CLI. You can also install the Edge Impulse CLI, which we have done before on another micro session, but we won't need it for this particular demonstration. However, if you're not using Chrome or Microsoft Edge, you will need the Edge Impulse CLI. Follow the directions here to connect the development board to your computer and download and update that Arduino board with the latest Edge Impulse firmware. I have shown you how to do this on another webinar, so hopefully you have done that and you're ready to go with the Edge Impulse firmware running on this Arduino board. When you are done with that, head to edgeimpulse.com. you will want to click Login and create an account if you have not already done so. I'm going to click Login, and this should bring me to my demo account. Here, I'm going to create a new project. In this case, I'm going to call it my Sensor Fusion. I don't need to pick a particular type of project. We are going to be using Sensor Fusion here. Head to Data Acquisition. If you are on Chrome, or if you are on Microsoft Edge, you can use Web USB to connect to your dev board. If you are not on either of those browsers, you will need to run the Edge Impulse daemon as shown in the other webinars in order to connect your dev board to your computer and then connect that to the project we just created here. However, Web USB is very easy, so I'm going to click that. I'm going to click my Nano 33 BLE Sense and click Connect. If you run into any problems with it, like I just did, you will want to disconnect the board from your computer and connect it back in. When it's done, let's try that again. I will click up here to connect to my board. And hopefully, with any luck, you should see the device enumerate here. One thing about the Magic Wand demo, if you have done it previously, is you will notice that we did very simple gestures. This was maybe a snake gesture, or a wave, or it sat idle. One of the things the accelerometer does not do very well is these twisting kinds of motions, like this. This is because the z-axis of the accelerometer, or excuse me, probably the y-axis here, points down, and then I've got my other axes pointing out and to the side. So when I twist it, the direction that is being pulled on by gravity never changes, so it can't really learn what that gesture looks like. This is where we pull in data from another sensor, in this case the gyroscope, which can pick up on these twisting types of motion, these angular momentum motions. And we can use that information combined with the accelerometer in order to do more advanced gestures so we can actually twist it and move it. We're going to keep it very simple for now. We're going to do 3 different types of gestures. The first is just going to be this twisting motion. That's actually very difficult with the accelerometer alone. We're going to do a circle like this, and then we're going to do idle where we just leave it on the table and collect a bunch of data. We will use anomaly detection to determine if some type of gesture was seen that was not one of those 3. To start, I'm going to create a label that says twist. Leave the sample length and frequency fields as default, and we don't want just the accelerometer. We want inertial. This is the IMU, or the inertial measurement unit, that's on the Arduino Nano 33 BLE Sense. Before, we were just using the accelerometer. That's part of that IMU. We will be using both the accelerometer and the gyroscope. We will not be using the magnetometer in this case. The magnetometer is used to find an absolute heading based on the Earth's magnetic field, or it can be messed up pretty easily using any ambient magnetic fields I might have around me, such as speakers or electronics. Once we have that selected, go ahead and grab your board, click Start Sampling, and when you see that, just make a twisting motion like this. Try to keep it as vertical as possible, and you can do it with different speeds, but try to keep that twisting motion going. I'm going to go ahead and repeat this until I get about 3 minutes of data. You'll want to aim for about 3 minutes of data per label. Now that I have my 3 minutes for the twist, let's create a new label. I'm going to call this one circle. I'm going to click Start Sampling, and once it starts, I'm going to hold my board like this and kind of make these sweeping circles, and I recommend trying both directions for this. You can twist the board a little bit, but generally you'll want to keep it in one position. The twisting motion will get picked up. It will help you create a more robust model, but for our demonstration, try to keep it more upright. Go ahead and continue this process until you get 3 minutes of data collected for your circle label. Once you've collected your 3 minutes for the circle label, Let's do it again, but we're going to do a label for idle. In this case, I'm going to take my board, and you can either hold it in your hand, or I'm going to put it on my desk beside me and just kind of let it sit there. When you're doing this, try not to move it. It can sit this way, it can sit this way, it can sit this way, it can sit this way. Just try not to move it. That's the big thing here. We don't want any acceleration spikes or gyroscope spikes to show up for this data. So I'm going to put it on the desk behind me, and I'm going to click Start Sampling and just let it sit there. The reason we want to do multiple orientations is because we want to train a more robust model that will recognize that the board is idle in these orientations. That being said, what you will probably find is that when we go to do our feature extraction or our pre-processing with the DSP block, it's going to be looking for various frequencies anyway, and any DC component, in this case the orientation of the board, is probably not going to matter a whole lot because it's not moving, but recommended to collect that data to create your robust model anyway. I'm going to finish by collecting the full 3 minutes for this idle, and I will be right back. When you're done with that, you'll probably notice that all of our data is in the training test set. What we'll want to do is have the tool split it between training and test. So let's go to Dashboard. We're going to scroll down and click Perform Train Test Split. This is going to automatically randomly split our data between the training and test data sets. So click that and type Perform Split. You can go back into data acquisition, and you should see about 80-20 split between training and testing. Make sure you've got 2-ish to 2.5 minutes in your training set. If you go to your test set, make sure you've got about 30 seconds-ish in each. It's going to be randomized, so it's okay if it's a little more or a little less. Feel free to click on one of your samples and get an idea of the sensor data. It's a good idea to play with your sensor data. So let's take off idle because that's going to be fairly boring straight lines. We can look at circle, and you can see here how our gyroscope moves through the circle and a little bit of how our accelerometer oscillates as we made that circular motion. If you click on twist, you should see that the accelerometer data doesn't really move at all. Instead, our gyroscope data, especially the gyroscope X, so it does look like it was X that was rotating as we twisted the board. That's going to give us an indication of how the board was moving through space, and hopefully the neural network will pick up on that. As opposed to using just the accelerometer data, now we can do more advanced motions. Let's go to Impulse Design, and we want to click on Add Processing Block. Let's click Spectral Analysis. Here you can select the different axes, or in this case, the various sensor data that's going to be fed into our spectral analysis block. In this case, it's going to perform some digital signal processing. The output of that will go into our neural network. We want our accelerometer data, we want our gyroscope data, but we don't need magnetometer. So deselect those. Let's click to add a learning block. We want to do classification. This is a basic Keras neural network that we're going to be creating. And let's add another. In this case, we want to do anomaly detection. You can leave these as default. Make sure that the spectral features are being fed into them so that these checkboxes are checked. Click Save Impulse. Go to Spectral Features. You can look at your features here again from your raw sensor data. Notice that the magnetometer has been dropped. All of the defaults should be good. Click Save Parameters and click Generate Features. Wait a moment while that generates all of the features. Once the features have been generated, feel free to look at the Feature Explorer. Hopefully the different classes are grouped together and separated from one another. In this case, our idle is fairly close to twisting, so there might be some confusion here, but there should not be much confusion between the circular motion and the twisting and idle motions. Let's head to NN classifier to train our neural network. I like to do a few more training cycles or epochs, so I'm going to type in 100 here. The basic model should work for this case, so click Start Training and you should see the output of training appear on the side here. I'm going to step away for a second and let this train. I will come back when it is done. When it's done, scroll down and take a look at the confusion matrix. Sometimes you might run into instances where it looks like your model is not performing very well. In this case, where the actual label is idle, it starts to predict it as circle. If you scroll up in your training log, you can see that the validation and training accuracy were 0.99, or very close to 100%. So this doesn't make a lot of sense. If you run into this, there's a good chance you're seeing quantization error. And this is because we're quantizing the models because they should work a little faster on many embedded systems. You lose a little bit of accuracy sometimes, but often it's enough to get the job done. In this case, it looks like the quantization error is enough to wreak havoc with our model, and we need to try the floating point version. So let's try the unoptimized version, and sure enough, there's that 99.8% accuracy that we're seeing. This is going to have to be good enough for now with our default model. You could try dropout layers, you could try making your model bigger, but if we want to use a smaller model, we probably have to go with this floating point version. Next, head over to anomaly detection. It will star for us the values or the axes that it thinks is important. So let's go ahead and select those. We do want the acceleration, and we want to enable the gyroscope for anomaly detection. And these are the RMS values, or root mean square. So select all of those, click Start Training. Training should be pretty fast for this anomaly detection, as it's doing simple clustering. When it's done, you should see where the clusters are. The idea is if we make a gesture and it's outside of one of these clusters, it will be flagged as an anomaly. That's how we can tell if we're doing one of the gestures that we have not trained for. Now it's time to test our model. Let's first head to Model Testing and click Classify All. These are the collections of gestures that were in the test set that we initially set aside, the about 20% of our data set. Ideally, we never looked at them, otherwise we might introduce bias or some type of overfitting into our model. And since we have not used them in training, we can test our model on them to see how well it performs with unseen data. As you can see, it works decently well. We got over 90%, which is really good. It struggles a little bit between twist and idle. And in fact, we can take one of these where it misidentified it or misclassified it, click Show Classification, wait a moment, and when that pops up, we can see what's going on. Oh, it looks like I bumped the board here. Remember that part where I said don't bump the board? That's exactly what happened, is I bumped the board and it gets misclassified as a twist. So this is what happens when you have bad data because you accidentally did something. It can really mess up your training or testing. In this case, it was testing. However, 90% is good enough to try. So I'm going to head back to Live Classification. I'm going to click Connect with Web USB, click Pair. My Arduino board should show up. Make sure all of these values look correct. And what I'm going to do is when I click Start Sampling, I'm going to twist it above, do a circle, make some random motion, and put it on the table or my desk behind me. So I'm going to click here. Once it starts, I'm going to twist it. I'm going to then make a circle motion both directions. I'm going to then do something random with it and put it on the table. Hopefully I was able to get it on the table fast enough so that you can see that idle. And up here in this first part, sure enough, there's a twisting motion. No anomalies detected. As we move over, we can see that there are anomalies detected as I'm transitioning from that twisting motion into the circle. That's an unknown motion. And it looks like a lot of this was anomalous, interestingly enough. Even the circle motions. It did catch the idle at the end, and there's a good chance this happened because the window wasn't long enough. So I'm going to try this again, But it does look like it was classifying. It was just classifying it as anomalous, except for that twist motion. Click Start Sampling, and when it starts, I'm going to do a twist. I'm going to do a circle, and I'm going to put it on the table. Let's see if that works a little better. The twist had one anomaly, but otherwise it looked pretty good. There was a transition period here where you can see it as anomalous data, but I was able to capture the circle and not be an anomaly. And then as I was moving, it was anomalous. It thought it was circle, but you can throw this data away if it shows up as an anomalous data over some threshold of this anomaly score. But at the very end, I was able to get it to the table fast enough where it still thinks it's circle. I had you can see over here the window is not short enough, or I didn't get it to the table fast enough. So to make sure we get that idle, I'm going to sample again. And I'm going to twist it. I'm going to do my circle. And I'm going to get it down to the desk behind me and leave it there. Hopefully for long enough this time. Third time's a charm. And here we go. I've got the twist, not an anomaly. It is an anomaly as I transition into that circle. It looks like I did not perform the circle well enough, except for one window over here. I was performing the circle the best. Otherwise, it was not a great circle in this case. But towards the end, I was able to get it down to the table. And sure enough, it is idle without being an anomaly. So it does work. I probably just needed a little longer than 10 seconds to demonstrate each of those classes as they should be working.